Now then, whilst browsing the Twitter earlier today, I came across this tweet. It's an article that was tweeted out by Quantum Magazine. The electron is so round that it's ruling out new potential particles. Potential new particles. There we go. So let's just jump into the dealio, shall we? Oh, we shall. All right. Link is in the doobly-doo, of course. Oh, look at that. Look at that. That's a compass. I remember using one of those back in the day. But yeah, you put the thing down, you twirl it around, it makes basically a circle if you could do it as well as you could. The subnote: if an electron were the size of Earth, the experiment could detect a bump the size of a sugar molecule. That's a pretty good experiment, in my opinion. Imagine an electron as a spherical cloud of negative charge. If that ball were ever so slightly less round, it could help explain fundamental gaps in our understanding of physics, including why the universe contains something rather than nothing. Given the stakes, a small community of physicists have been doggedly hunting for any asymmetry in the shape of the electron for the past few decades. The experiments are now so sensitive that an electron with the size of the Earth, they could detect a bump on the North Pole the height of a single sugar molecule. Again, that's some pretty dang good precision. The latest results are in. The electron is rounder than that. Wow, that's pretty neat. The updated measurement disappoints anyone hoping for signs of new physics, but it still helps theorists to constrain their models for what unknown particles and forces may be missing from the current picture. Quote, I'm sure it's hard for the experimentalists measuring zero all the time, but a null result in this experiment is really valuable. It really teaches us something, unquote, says Peter Graham, a theoretical physicist at Stanford University. The new study is a technological tour de force. It is also very important for new physics. Poaching elephants. The means of the structured channel does not promote the poaching of elephants. Elephants are people too. The standard model of particle physics is our best roster of all the particles that exist in the universe's zoo. The theory has held up exceptionally well in experimental tests over the past few decades, but it leaves some serious elephants in the room, says Dmitry Butker, a physicist at the University of California, Berkeley. For one thing, our mere existence is proof that the standard model is incomplete, since according to the theory, the Big Bang should have produced equal parts matter and antimatter, and that would have annihilated each other. In 1967, the Soviet physicist Andrei Asarkov proposed a possible solution to this particular conundrum. He conjectured there must be some microscopic process in nature that looks different in reverse. That way, matter could grow to dominate over antimatter. A few years before, physicists had discovered such a scenario in the decay of the kaon particle. That alone wasn't enough to explain this asymmetry. Ever since then, physicists have been on the hunt to find hints of new particles that could further tip the scale. To do so directly using the Large Hadron Collider. Navntata is the most complicated machine ever built. But over the past few decades, a comparatively low-budget alternative has emerged, looking at how hypothetical particles would alter properties of known particles. You see footprints of new physics, but you don't actually see the thing that's made of them, says Michael Ramsey Musoff, a theoretical physicist at the University of Massachusetts Amherst. Now, I'm not a professionally trained theoretical nor particle physicist. I'm a dude on the internet, but I think he's talking about what was it, the Higgs boson? Because that's one of those things where it's like we measure these things and then we look at the area where there is nothing. That's where we're like, that must be where the Higgs is. Hey, Monterey, thank you for joining, my friend. One sense potential footprint could appear in the roundness of the electron. Quantum mechanics dictates that the inside electron's cloud of negative charge. Other particles are constantly flickering in and out of existence. The presence of certain virtual particles beyond the standard model. The kind that could help explain the primordial supremacy of matter. It would make the electron's cloud look like slightly more egg-shaped. One tip would have been a bit more positive charge, the other bit a bit more negative, like the ends of a bar magnet. The charge separation is referred to as the electric dipole moment, EDM. It's also pretty good music out here. The standard model predicts a vanishingly tiny EDM for the electron, nearly 1 million times smaller than what current techniques can probe. So research tried to detect an oblong shape using today's experiments. That would reveal definitive traces of new physics and point toward what the standard model might be missing. To search for the electron's EDM, scientists look for change in the particle's spin, an intrinsic property that defines its orientation. Electron spin can be readily rotated by magnetic fields, with its magnetic moment serving as a sort of handle. The goal of these tabletop experiments is to try to rotate the spin using electric fields instead, with the EDM as the electric handle. The quote is, if the electron's perfectly spherical, it's got no handles to grab onto to exert the torque, says Amar Vutha, a physicist at the University of Toronto. But if there's a sizable EDM, the electric field will use it to tug on the electron spin. We have another quote. There are words to express my admiration of this cleverness and persistence. It's just the best science there is. Welcome, Rit. Good to see you, my friend. But let's quote from Dmitry Bukur, the University of California, Berkeley. So let's basically the big thing is physicists to look for different things. Now, if there was some more sim trailing, I'm just strictly conjecturing as I do it on the internet, that if you could see something, there must be something else going on there, so we could find new things, get new clues. But if we have to deal with and work with what we've got, only we could find a way to help connect the really big and the really small. I got hope. In 2011, researchers at Imperial College London showed that they could amplify this handle effect by anchoring the electron to a heavy molecule. Since then, two main teams have been leapfrogging one another every few years with increasingly precise measurements. Kind of reminds me of the Monday Night Wars that Monday Night Raw and Nitro had. Good old Attitude Era days. Don't condone everything. Totally influenced me. One experiment now at Northwestern University goes by the name of Advanced Cold Molecule Electron EDM, or ACME. I love it. A background inspired by the old Roadrunner cartoons. I love those. Another is basically uses the Colorado's JILA Institute. The competing teams' measurements have jumped in sensitivity by a factor of 200 in the last decade, with no EDM to be seen. It's a sort of race, except we have no idea where the finish line is or whether there is a finish line even. So David Melville, a physicist at the University of Chicago and one of the leaders of the ACME group. Welcome, Light Chapel. We're just discussing ACME, or Roadrunners, and potential electron dipole moments that may be used as a handle potentially. I probably butchered that. I apologize. A race to the unknown. To keep trekking ahead, research wants two things: more measurements and longer measurement time. The two teams take opposite approaches. The ACME group, which set the previous record in 2018, prioritizes quantity of measurements. They shoot a beam of neutral molecules across the lab, probing tens of millions of them every second, only just for a few milliseconds each. The JILA group measures fewer molecules, but for longer. They trap a few hundred molecules at a time and measure them for up to 3 seconds. Oh, that's actually a pretty long time. The ion trapping technique, first developed by Eric Cornell, physicist at the University of Colorado Boulder, who directs the JILA group, was a big conceptual breakthrough, DeMille says. Many people in the field thought this was nuts. Seeing it come to fruition was really exciting. Having two distinct experimental setups that can cross-check one another is absolutely crucial, Budiker says. I don't have words to express my admiration for this cleverness and persistence. It's just the best science there is. Cornell's technique was first showcased in 2017 with hafnium fluoride molecules. Since then, technical improvements has allowed the group to suppress ACME's record by a factor of 2.4. I'm not even sharing the article, am I? I am the worst person in the world. Wow. Oh, man. In a recent preprint led by Cornell's former graduate student, Tanya Rusi, the team declined to comment while their paper is still under review at Science. Well, that's the end of the article anyway, so. Well, see, that's the type of stuff I like. It's like, all right, we've got some experiments. What are we looking for? We don't know. Let's just keep probing, and you're coming at it from different angles. Because if you're all doing the same thing, it's like, oh, don't you want to keep checking and cross-checking and stuff like that? Aren't these things that, I don't know, inspire competition, inspire ingenuity, inspire folks to, I don't know, I'm not wearing a level up shirt right now just because I just took it out of the laundry. But I just thought that was an interesting article. There's something to bring to y'all. So Very exciting things happening. And again, rumor has it, 2023 is the year to see. But that's all we got for right now. Take care of yourselves.